All right, so here we go. This is problem number 78 from chapter 4 of the Halliday and Resnick textbook. So we've got this figure. The hardest thing about this figure is just keeping straight what's what. So we've got two Jeeps, and for some reason they've called one of the Jeeps P, and they've called the other Jeep B. All right, and they're both going to race along straight lines, like it shows here in the drawing. And then they go past a stationary border guard whom they've called A. So the guard is at point A. So the big thing to notice is that he's stationary, okay? So that's the deal there, okay? So it tells you that relative to the guard, B travels at a constant speed of 20 meters a second at an angle of 30 degrees. So here's the deal. So the velocity of B, the Jeep, relative to the guard, A, is 20 meters a second at 30 degrees north of east. So I right away just rewrote that in unit vector notation. So that becomes the same thing as 17.32I plus 10.0J. Again, I always hang on to a couple extra sig digs. And what is this? This is all in meters per second. All right, so that's the velocity of B relative to A. All right. Then the next thing it says is relative to the guard, P has accelerated from rest. So the velocity of P relative to the guard initially is 0. All right. And then it tells you that the acceleration of the guard, the acceleration of P is this, right? So rather than, I guess you could do this. So the acceleration of P relative to the guard is 0.400 meters per second squared. So what that really tells me is this, that the velocity of P relative to the guard at time t, being a little sloppy about my units here, is going to be 0 plus my acceleration times time, right? Vi plus a times t. So it's just going to be 0.400 t, right? So that's the velocity of Jeep P with respect to guard A at time t. Okay? But it's at this angle, right? At 60 degrees, north of east, right? Yeah, 60 degrees north of east, right? So same thing here. This is going to be at 60 degrees north of east, right? Because you're going to, if he starts at rest, the direction you accelerate in is the direction you end up moving. All right? So at a certain time during the acceleration, P has a speed of 40 meters a second. Aha! So the question is, how much time is it going to take to get up to, do this in a different color. The question is, how much time is it going to take to get up to 40 meters a second? Well, you can just kind of do the math, right? Plug in 40 equals 0.400t and divide, and you find out that your time is 100 seconds. So that's the time that ultimately we're going to be interested in. Okay? Because all of the questions say at that, well, not all the questions, but question A says at that time. So when we say at that time, that means t equals 100 seconds, right? Okay, so that's kind of our starting point. So let's clear up some space here on the board. All right, so we freed up some space on the board here. So, all right, so the next thing we got to do, let's answer the question. Question A wants to know, what's the velocity of P relative to B? Well, so all of our stuff over here is sort of relative to A. So let's do this. We know that the velocity of P relative to B is the velocity of P relative to A plus the velocity of A relative to B, right? And we're talking about at that time. So we want to remember our time that we're talking about here is t equals 100 seconds, right? Let's do this. So at that time, I'm going to that's sort of our final time, right? So at t equals 100, here are the things that I know. I know that the velocity of p relative to a is, from over here, oh, well, that was given to us. Remember, that was 40 meters a second, right? At 60 degrees north of east, right? So again, we need to write that in unit vector notation. So if you do that, you end up getting 20I plus 34.64 J, and that's all in meters per second. Okay? So, and again, that's just by, doing your vectors, right? Okay, so let's kind of clean this up. I don't really need this 40 meters a second here. I kind of want to make a little table here, so you'll see where I'm headed here in a second. All right, let's move this guy over here. Okay, so there's our velocity of p with respect to a at time 100. And we know that the velocity of a with respect to b, do we know that? Sort of. So over here, I know the velocity of b with respect to a. So remember the velocity of a with respect to b, is just going to be negative velocity of b with respect to a, right? So all I'm going to do is I'm just going to use these numbers but make them negative, right? So that's going to be negative 17.32 I minus 10 J meters per second, right? So we can now use all of this stuff. Scroll down. So remember, we want to scroll too far. So remember, we want to add VPA plus VAB equals what we're looking for, right? So the velocity of P with respect to B is what I get when I add these guys, right? So just add component-wise, and you end up getting 2.68 I, and then 34.64 minus 10 gives you 24.64 J, and this is all in meters per second. Okay. And then you just draw your triangle, and you do your Pythagorean theorem and find your angle, right? Because we've got our x component and our y component. So the velocity of p with respect to b at t equals 100 seconds is, you end up getting 24.8 meters a second at 83.8 degrees north of east. Okay? So that is part A. Now, part B, there's two ways of doing it. Part B says find the acceleration of p relative to b. So in order to do that, I want to use the acceleration equation, right? So let me do this. Let me, as usual, free up some space on the board. Okay, so so we're trying to find the acceleration. Let me do this in, blue. We're trying to find the acceleration of p relative to b, right? So remember, acceleration is your final velocity of p relative to b minus your initial velocity of p relative to b divided by the time that took. Now we know the time is 100. We know that the velocity of p relative to b at time 100 is this guy. So we just got to find the velocity of p relative to b initially. So, do we know that? All right, so the answer is no, we don't know that. We need to find it. All right, so I'm sort of going through more work than I need to, but I think there's value in doing this. So kind of bear with me here for a minute. If you're at home sitting there shouting, we already know the acceleration, I know, but I want to show you that it works. All right, so what we need to do now is we need to find the velocity of p relative to b initially. Well, that's the velocity of p relative to a initially plus the velocity of a relative to b initially. So here's what we know. We know that the velocity of p relative to a initially is just 0. So 0I plus 0j. And I know that the velocity of A relative to B initially is, oh, well, remember, that's this guy, but you got to make it negative, right? So that's the same thing we just did a minute ago. So it's negative 17.32 minus 10, I and j. So we can add those to find out that the velocity of P with respect to B initially is negative 17.32I minus 10j. Cool. So there's that. All right, so now we just got to plug our numbers into the equation, right? So here we go. Let's see. So the acceleration of P with respect to B should be my starting velocity, which was this guy. So here we go. We're going to have, I'm going to move down a line. It's 2.68I plus 24.64J. This is all in meters per second, minus my initial, which is this guy, negative 17.32I minus 10J. And the whole thing is over, what, 100 seconds, right? All right, so we're almost done here. So let's see, if you simplify this mess, you end up getting, when you combine your I components, you end up getting 20I. Sorry, I probably should have put meters per second on all of this. So you get 20I when you combine your I components. And when you combine your X component, when you combine your J components, you get 34.64 J meters per second over 100 seconds. So this gives you 0.200 I plus 0.346 J meters per second squared. And then we're just looking for the magnitude of the acceleration, right? So, do your Pythagorean theorem. So we know our horizontal acceleration is 0.2, our vertical is 0.346. Find your hypotenuse, and the acceleration turns out to be 0.400 meters a second squared. All right. Now, we didn't have to do all that. Because look, what we just did is we found the acceleration of P relative to B, and remember, B has a constant speed. So this is the acceleration of P relative to B, sorry. Remember, B is traveling at a constant speed. Oops, that's not what I need to do. There we go. B is traveling at a constant speed. So remember, anytime you're traveling at a constant speed, that doesn't sort of affect your acceleration. And we knew that the acceleration of P was 0.4 meters a second squared relative to the guard, who's also at a constant velocity of 0. So B, you really don't even have to do any work for. You just go, oh, well, the acceleration of P relative to the stationary guard is 0.4 meters a second squared. And since B is also moving at a constant velocity, it's the same acceleration. So you really don't even need to calculate all this. You just go, oh, well, it's the same thing, because both of the velocities are constant. But I do think that there's value in understanding that mathematically it works out. Okay, there you go. Very long explanation.